Hello student. Today we will discuss about the chapter shear and bond in RCC design. Now we know that concrete is very weak in taking tension. So wherever there is tension in a member, we must provide steel reinforcement. We must introduce some steel bars which will help concrete in taking tensile stresses. Like in the previous chapter in design of singly reinforced beam, as the beam is subjected to sagging bending moment, we provided steel bars at the bottom to take the tensile stresses. Now in a beam, there is bending as well as shearing action. In mechanics of structure, in second year we studied SFD and BMD, shear force diagram and bending moment diagram. The shear force is introduced in a beam. In this case, it introduces the diagonal tension. You can see in this sketch, the rectangle is stretched and one diagonal is in compression. This diagonal of this rectangle is under compression. The length is reduced, whereas this diagonal is stretched. It is under tension. You can see that tau is the shear stress and tau dash is the complementary shear stress. And this shear stress produces diagonal tension. And to resist that diagonal tension, we must provide steel reinforcement, which is called as shear reinforcement. And the shear reinforcement may be in the form of stirrups, vertical or inclined, or bent up bar. We know that the shear stress produced in a beam is Fa y bar upon Ib. This we studied again in mechanics of structure in the chapter bending and shear stresses in the beam. So, shear in a beam is caused due to change of bending moment in the span. For a beam of homogeneous material, the shear stress is given by tau is equal to Fa y bar upon Ib. In case of reinforced concrete beam, the concrete below the neutral axis is neglected being in tension. So, as we know, concrete is very weak in taking tension. It below the neutral axis, in case of sagging bending moment, entire concrete is neglected. The shear is assumed to be resisted by the bond between concrete and steel. The shear stress in RC beam varies parabolically with zero value at the top compression phase, reaching maximum value at neutral axis, and from neutral axis up to the center of AST, it remains constant, reducing abruptly to zero at the center of AST. Now this is the shear stress distribution diagram for a homogeneous beam. Here we get shear stress 0 at top and bottom and maximum tau c max at neutral axis. Whereas the speciality of RCC beam is it is a parabola. Shear stress distribution diagram is a parabola from top to neutral axis where concrete is in action, and below the neutral axis it is constant, and at the center of AST it changes abruptly and becomes zero here. So this is the speciality of shear stress in RC beam. Now the nominal shear stress tau v is calculated by the formula Vu upon Bd. What is Vu? Vu is factored shear force. B is width of the beam. You can see it is shown in the sketch, and small d is effective depth. So shear force upon area, you will get nominal shear stress. After finding the nominal shear stress, the next job is to check whether this nominal shear stress is not greater than tau c max. What is this tau c max? Tau c max is the maximum shear stress in concrete. It depends upon grade of concrete, and it is given in table number 20 of IS 456 2000. See this table number 20. In this table number 20, you can see This is the table number 20. You can see that grade of concrete M15, M20, M25, M30 and M35, M40 and above. Correspondingly, tau C max values in Newton per mm square are given. For M15 it is 2.5, for M20 it is 2.8, for M25 it is 3.1 and so on. So, as soon as you calculate the tau V, that is the nominal shear stress, your next job is to find or to confirm whether this tau V is less than tau C max or not. Then, when it is confirmed that tau V is not greater than tau C max, we can proceed. Then we will find shear stress taken by concrete, tau C. This tau C depends upon grade of concrete and percentage of steel provided on tension side. I will repeat, tau C is shear stress taken by concrete. It depends upon grade of concrete and percentage of AST. Table number 19 of IS code indicate these values of tau C. Now here you can see that here there are M15, M20, M25, M30, M35 and M40 and above. These are the grade of concrete. This shows the percentage of AST, that is PT. These values indicate PT and corresponding values of tau C we can find. Suppose for M15 grade concrete and PT is 1%, the value of tau C is 0.6, or for M20 grade concrete and percentage of steel is say 2%, the value of tau C is 0.79. If the value of percentage of steel is in between these values, suppose if it is 0.8, 0.8 means between 0.75 and 1. So by interpolation, we can find the value of tau C. So table number 19, this table number 19 gives us the values of shear stress taken by concrete. Now we will compare in the next step the value of tau V, that is nominal shear stress, to tau C. If tau V is less than tau C, no shear reinforcement is required. See, whatever is the shear stress coming in the beam, that is tau V, is less than the capacity of the concrete. So no shear reinforcement is required. But IS 456-2000 recommends to provide this minimum shear reinforcement. What is that minimum shear reinforcement? We will see afterwards. If tau V is greater than tau C, you will have to design the shear reinforcement in the form of vertical or inclined stirrups and bent up bar. Bent up bar are optional, but vertical stirrups are compulsory. Now, what is this minimum shear reinforcement? That I will explain. See, this minimum shear reinforcement is given in IS 456 clause 26.5.1.6. IS 456-2000 specifies the provision of minimum shear reinforcement in the form of vertical stirrups for the following reasons. 1. To prevent sudden failure and provide ductility to give warning of failure. Second, to prevent premature failure if the bond to maintain steel is lost due to busting of cover. Third, to act as tie for the beam reinforcement in position. And fourth, to confine the concrete. For these four reasons, IS code specifies to provide minimum shear reinforcement in the form of these vertical stirrups, in which spacing minimum, S minimum means spacing of the stirrups minimum, must be equal to 0.87 FY ASV 0.4B. Here Fy is the grade of steel. If it is Fe415, then Fy is 415. B is the width of the section, and ASV is the cross-sectional area of the stirrups. Here, if you are providing two-legged stirrups, then ASV is equal to number of legs 2, 2 into pi by 4 d square, where d is the diameter of the bar used for the stirrups. This is three-legged stirrup, and you can see it is four-legged stirrup. See, 1, 2, 3, and 4. This is two-legged 1, 2. This is three-legged 1, 2, three-legged stirrup. So likewise, we will calculate the area of stirrups ASV number of legs into pi by 4 d square, where d is diameter of the bar used for stirrups. Then there is another clause given by IS 456, that is clause number 26.5.1.5, that is maximum spacing of shear reinforcement. You cannot provide stirrup spacing more than this. The maximum spacing must be less than 0.75D or 300 mm, whichever is less. I will repeat, the spacing of stirrups should not be greater than 0.75D or 300 mm, whichever is less. Now, how to design a shear reinforcement? These are the steps to be followed for designing shear reinforcement for a beam, rectangular beam. First, calculate a nominal shear stress, tau V, which is equal to Vu upon Bd. What is Vu? Vu is factored shear force. Then step 2, check for tau C max. This tau V should not be greater than tau C max. Then next step, calculate tau C. Calculate tau C considering grade of steel and PT percentage of steel from table number 19 of IS 456 2000. In examination, this table or the abstract or the required range of PT and grade of steel will be given. So don't worry about that value, or directly they will give you the value of tau C in examination. Now, if tau v is less than tau c, no shear reinforcement is required, but provide minimum stirrups for spacing. S minimum is equal to 0.87 Fy ASV upon 0.4 B. If tau v is greater than tau c, design shear reinforcement. Calculate shear to be taken by shear reinforcement Vs. Vs is equal to Vu minus tau cbd. We know that tau c is the shear stress taken by concrete, which is calculated from table step number 3, table number 19. Then once you find the shear to be taken by shear reinforcement, that is Vs, you can design only stirrups or stirrups plus bent up bar. Now shear which is taken by vertical stirrups SV is VUSV is equal to, considering that you can find the spacing of the stirrups SV equal to 0.87 Fy ASV into D divided by, this is the shear to be taken by vertical stirrup, that is VUSV, and this is the shear force taken by bent up bar VUSB is equal to 0.87 Fy ASB into sine alpha. In no case, VUSB should be greater than zero point 0.5 times Vs. So, whatever is the shear force to be carried by shear reinforcement, the bent up bar should not carry more than 50% of that. Then, step number 4, check for spacing of stirrups maximum, that should not be greater than 0.75D or 300 mm, whichever is less, and check for S minimum also, that is 0.87 FYASV upon zero point 0.4 B. So these are the design steps of shear reinforcement. In the next lecture, we will actually solve some numerical problems of design of shear reinforcement. Thank you.